This is a demo recording for the Unacademy's Star program. Hello, everyone. My name is Nikunj, and I welcome you all to this wonderful and a very interesting session on one of the very important topics of important as well as interesting, of course, topics of the JE Foundation, and that's mechanics and kinematics. Today in the class, we're going to discuss about the basics of mechanics and kinematics, and the basics start with what we already know as motion. So we're going to take up the topic motion today, and we'll be discussing very briefly about what exactly it is and the other things. Let's see the table of content that we have for the topic of the chapter or the session that we'll be taking up today. So this is what the table of content looks like. We will be going from defining motion and rest. That means to understand what exactly are motion and rest, how to define them, and how they are relative, or what do we mean when we say motion and rest are relative. That's our first topic of discussion. The second topic of discussion is going to be measuring motion, and the third one would be representing motion. Now if you see the flow that has been arranged, or the flow that it has been following, you'll see a particular pattern in them, and that's exactly what the scientists also follow whenever they discover a new topic. Whenever they discover a new topic, let's say for example gravitation, whenever first gravitation was discovered, first they wanted to define and understand about gravitation. Once that was done, then they want to quantify, or they wanted to quantify gravity or gravitation, or basically measure gravitation. And then finally they wanted to represent the gravitational forces and the gravitational fields with different diagrams that you already know about. Similarly, we're going to understand about motion, then we're going to measure motion, and then we're going to represent the data that we have when we measured motion in the second step, right? So this is what the flow of today's session would be. Let's quickly jump into the topic and dive a bit deeper into this very interesting and a very important topic from the JE Foundation point of view. Let's start. So first topic is defining motion rest. Now, anyone here who can define motion and rest, or who can tell me what do you understand when you hear the word motion and rest? How do you define it in layman language, in very rough language? Anyone, any idea? Well, I've got some responses. Let me put it in technical terms. It's very easy to define motion and rest. And if you have seen if you can see in the braces, I've written the split personality or the concurrency. We'll discuss about that. What does it mean basically? It's a lame joke that I wanted to crack. So motion and rest are basically, this is how you define them. Motion, a change in position of an object with respect to surrounding and time. Very simple. Whenever an object is changing its position, that's said to be in motion. And if it is not changing its position, that is said to be at rest. So if I put it in words, this is how you define motion rest. Change in position of an object with respect to, mind you, WRT here is an acronym for with respect to its surrounding or time. And when you say rest, it's basically no change in position of an object with respect to its surrounding or time. Now you might say, sir, why are you complicating things? Why do you have the word surrounding and time here? Why can't we simply say change in position is motion, change is no change in position is rest? Why do we need those complicated words, surrounding and time, that are making the definitions long for no good reason? Well, we'll talk about it in just a moment. Now, having understood about the definitions of motion and rest, if I ask you the question, are you in motion as of now? You might say, sir, no, we are all sitting at our places. Why are you asking this very simple question? We're all simply sitting at our places and taking this lecture. That means we are at rest. We are not changing our position. The same applies to me as well. If you ask me the question, if I am in motion or rest, I am at rest, sitting on my chair, taking the session. So both of us, that means, are at rest according to each other. But if I were to ask the same question to an astronaut, let's say an astronaut who is sitting, let's say, in the International Space Station as of now, and we ask the same question to the astronaut, hey, astronaut guy, are we both in motion or rest at this particular moment? He's going to say, or she's going to say, guys, you are all on Earth. The Earth is constantly revolving and rotating around its own axis and the sun. And if you are on Earth, you are always, throughout your life, in motion. What did we just prove? We have just proved that a single object can be in the state of motion and at the state of rest at the same time, provided there are two different observers involved. These observers in technical terms are called as frame of references, or simply A reference. And you need a reference to be able to define motion rest. Something that is in motion for me. In reference to me, something is in motion. In reference to you, it might not be in motion. It might be at rest. So you need a reference, a frame of reference to define motion and rest. And these here are the most common frame of references that we take. Either you can tell that object is in motion with respect to its surrounding or with respect to 524. At 525, it has changed its position. So with respect to time, it's in motion. That is why you need the words surrounding or time in the definitions of motion and rest. And that finally brings us to our topic, and that is motion and rest are both relative. It depends on the observer whether something is in motion or rest. And therefore, next time if someone asks you whether that object is in motion or rest, tell him, bro, you need to tell me according to whom. You need to accompany one more question with it, according to whom. Because motion rest are defined differently for different observers, right? That's the basics of motion and rest. Now, having understood about motion rest, the next thing that we want to do is we want to quantify motion and rest. You want to measure motion. But then that's a very difficult thing to do, right? How do you measure something that you cannot see? You cannot see the amount of motion in an object. Definitely you can see an object in motion, but you can't see how much motion is it carrying with it. You can't see me. And if I've cracked the joke already, that's what motion is, John Cena. You can't see it, but you can definitely measure it. How do you measure it? How do you measure the amount of motion contained in a body? While basically you need to ask three very simple questions to yourself and you'll be able to measure the motion amount or the amount of motion in an object. The first question is, if something is moving, it must be traveling some distance or length. I'm not using the word distance, sorry. Some length. It must be traveling some length. The first question is, how far will it move, or how far has it moved? The second question you want to ask is, okay, it moved that far, but then how much time did it take to move that far? How fast did it go? That's the second question. And finally, the third question would be, how consistent it was while it was performing that motion. Right? So these are the three questions. And if you can answer these three questions, you'll be very easily able to answer or measure the amount of motion contained in a body. How far, how fast, and how consistent, please remember. And that tells us about the quantities that you need to measure motion. Basically, you need these five quantities listed here to measure the motion. You need to measure the distance traveled, the displacement traveled, the speed traveled, the velocity traveled, velocity with which it is traveling, and the acceleration. Now, I know you already know these words, you already know how to define them, but there's just, like I told, a foundation recap or a recall of your grade 9, grade 8 stuffs. So I'm going to quickly put it up in one lines. Distance is basically the total length of path that the object has traveled. How much length, whatever path it has traveled, if you measure the length of that path, that is distance, and it's measured in meters, the SI unit, and it's a scalar quantity. I hope everyone remembers what is a scalar and a vector quantity. Scalar quantities, quickly recall everyone, is a quantity that only has magnitude, of course, with a unit. Vectors, on the other hand, have magnitude, unit, as well as direction, right? So that is distance, and displacement is the shortest straight line path connecting the initial and final positions measured in meters, and it's a vector quantity. I'm not going in a lot of details about distance and displacement, assuming that you already know these terms. Speed is distance over time. This velocity is displacement over time, measured in meters per second, both of them. The only difference is speed, S for speed, S for scalar, V for velocity, V for vector. Speed is a scalar quantity. Velocity, on the other hand, is a vector quantity, right? So that is what is speed and velocity. And acceleration, it's a very easy word to remember if you can relate it to the accelerator on your bikes or your cars. This is a steering, sorry, cars. So the accelerator that you have on your bikes or on your cars, what do you do with it? When you press or when you increase the throttle of your bikes or the cars, of course, I'm only using bikes, please. Very difficult to use both those examples simultaneously. So if you increase the throttle of your bikes, what happens? Your bike speeds up. And if you reduce it, the bike slows down. That means acceleration does one purpose. Acceleration does one job for you. That job is it basically changes the speed of your vehicle depending on what you want to do, whether you want to increase it or decrease it. So acceleration is basically the change in velocity with respect to time, of course. Or it's also called as rate of change of velocity. And how do you find a change? What do you mean by change in velocity? Let's say you have bought something from me for $20 or 20 rupees. Now, and you've given me ₹100 note. How would I calculate the change that I need to give you back? 100 minus 20, of course, right? That means 80. What did you do? To find a change, you need to subtract. And that's what you're going to do for changing, to find the change in velocity. That's final velocity represented by V with a subscript F minus VI over T. So that is the acceleration formula, Vf minus Vi over T. And that is how you measure distance, displacement, speed, velocity, and acceleration. Very simple. This is measuring motion. This is how you can measure motion, right? Now, having understood about this, the next thing is you want to also find out a particular physical quantity out of these five if that is not given to you with the help of the things that are given to you. That means now you want to find the relationship between these five physical quantities, and that is done by equations of motion. So equations of motion come to rescue when you want to find a physical quantity with the help of other physical quantities, right? I like to call it the three musketeers because there are three equations of motion that will help you solve any kind of questions where a particular data is missing. So first equation is basically V equals to U plus AT. I'll tell you what these symbols mean. The second equation is S equals UT plus half AT squared. And the third equation is V square equals to U square plus 2AS, where V is the final velocity, everyone. U is the initial velocity. S, please do not confuse, is displacement. I'm not using the word D because that's not there in the textbooks. The textbooks say S is the displacement, NCRT, of course. T is the time. And finally, you have A, which is acceleration. I hope you know the units of all of them: meters per second, meter seconds, and meter per second squared. So these are the three equations of motion that will come to your rescue for solving any kind of questions. Most of the questions in motion in one dimension and two dimension. Not two dimension, one dimension. V equals to U plus AT, S equals to UT plus half AT square, V square equals to U square plus 2AS. Now, why do we have these only three equations? Why not four? Why not five? Why not eight? Why not only one? Well, see, everything that happens in physics or in science has a certain meaning. Just like I told you, right? How is the chronology arranged in our topic also? First, you understand about the motion, then you go to measuring it, and then whatever you have collected the data after measurement, you represent it. Similarly, these equations are designed in such a way that if you see the first equation, you won't find the word S. If you see the second equation, you won't find the word V. And if you see the third equation, you won't find the word T. In each of these equations, one of the parameter has been missed by purpose or purposely, so that if it is not given to you in the question, you can still find the fourth quantity with the help of the three quantities that are given. Yeah. So if U, A, and T are given, you can find V. If U, A, and T again are given, you can also find S. If U, A, and S are given, you can find V with the help of that. Right? So these are the three equations of motion. Now, there are certain textbooks where you will find two more equations. That means making it a total of 5 equations of motion. But trust me, those are not required if you know these three equations of motion itself. So that's about the three musketeers, the three equations of motion. Very, very useful equations and very important from the exam point of view as well. Once now you have calculated everything, you have measured motion, you have the data of distance, speed, velocity, acceleration, everything. How do you show that data to someone who can understand about it? You don't want to show it in the form of a table, otherwise it will be a very long table and a very, very messy one. So the best way of representing data, we all know, is the graphical way of representing it. Therefore, the data that you have collected from the measurement part can be represented in graphical form, called as the graphical representation of motion. To do this, basically, you draw three kind of graphs. The first graph is the position versus time graph. And with position, I mean it can be distance as well as displacement, because we are talking about one dimension only. Second is velocity or the speed time graph. Velocity and speed, same thing. Now, third one is acceleration versus time graph. Now, you might ask, sir, why are you saying velocity and speed are the same thing? If they are same thing, then why did you tell us the two different words in the first place? Why speed and velocity have two different spellings, or why there are two words if they mean the same? Well, they only mean the same in one dimension, everyone. Please remember, one dimensional motion, when the motion is happening only in one dimension, that means only one direction, either left or right, or either up and down, only one dimension, then there is no use of direction. You won't have any change in direction because these are all one dimension. And the only thing that differentiates, if you remember, if you recall, the only thing that differentiates distance and displacement is the direction. And if that is also same, then the two words are also same. Yep. So in motion in one dimension, distance is equal to displacement, speed is equal to velocity. Acceleration, of course, is anyway different. When it comes to two dimension, and we'll be coming to that part very soon because you have uniform circular motion coming up after this topic. So when you go to the two dimension, you'll have speed, velocity separated. They are two different things. Okay. So that's about the graphical representation. You draw three graphs, these kind of graphs, and then you can go on representing the data. And not only representing, by the way, you can also analyze the data to find a lot of different things. For example, using speed time graph, you can find the velocity by finding out the slope of the graph. The gradient or the slope of the graph tells you the speed when it is a position time graph or a distance time graph. How do you find a slope? I hope you all of you know how to find the slope. It's basically the rise over the run. That means how much rise has taken place in a particular interval of run. If you find that ratio, that would be your slope. Similarly, from velocity time graph, if you find the slope, you're gonna get acceleration. And if you find the area under the graph, you're gonna get displacement or distance. If it is 1D, it hardly matters. Okay, so that's about the graphical representation. We have already spoken about all these things in grade 9, so I'm not going into a lot of details. That's it. That's how you represent motion. You understand about motion first, then you measure it, and then you represent it. Right? That's all. Thank you so much for joining. And the next topics that you should understand about motion, if at all you are curious to know the next topic, should be force, everyone. Now you might ask, why do we need to switch from motion all the way to force? Because these are very, very, very interlinked topics. How are they interlinked? So let me grab something up. Yeah, there you go. So you can see the specs, right? It's placed on my hand. Now, if I ask you, is it in motion or at rest? You're gonna say it's at rest. How will it move? It's only gonna move when you apply. Oh, I was about to drop it. It's only gonna move when you apply force on it. Yeah, it's only gonna move when you apply force on it. That means force can change the state of motion or the state of rest of an object. And that is what our very own Sir Isaac Newton said in his first law of motion. An object in the state of rest or in uniform motion would continue to be in that state until and unless it's acted upon by an external unbalanced force. That means you need a force to make an object move if it is at rest, and to stop or bring an object to rest if it's already in motion. You need a force. That force should be an external and an unbalanced force. What do we mean by all these things? We'll take it up when we start forces. I hope you understood about motion, and I hope you have followed me throughout the session. Thank you so much again for joining the session. I'll see you soon in the next class. Till then, bye-bye. Take care. Keep learning. Hasta la vista. Adios. And I'll see you soon in the next class. Thank you again. Have a good day ahead. Bye-bye.